Hi everyone, and welcome to the second instalment of MinEx CRC vNews for 2022. Today we're going to talk about two aspects of our research at opposite ends of the spectrum. The first is single impact percussion experiments that are being conducted at Curtin University as part of our drilling automation and optimisation research. The second is the Delamerian sampling workshop, which is an important piece of work coming off the back of the Delamerian National Drilling Initiative. You'll hear from Anna Petz and Claire Wade, who will be telling you about the Delamerian sampling workshop. The purpose was to prioritise and come up with a sampling schedule for downstream analysis, including geochronology, isotope chemistry, and a whole range of techniques aimed at characterising the rocks from the Delamerian area and determining their mineral prospectivity. Victor, Thomas and Masood will be reporting on their unique experimental setup at Curtin University, where they're gathering data on single impacts between a percussion bit and rocks to determine the mechanics of drilling at the finest scale. These experiments will be used to build up a model of bit-rock interaction, which is vital to optimising percussion drilling.
The MinEx CRC National Drilling Initiative Delamerian Sampling Workshop provided an overview of the field data acquisition project and results. Geoscientists from MinEx CRC participant organisations were invited to establish projects to analyse and interpret these drilling samples. The Delamerian project provided a suite of geological samples from the Cenozoic Murray Basin through to the Cambrian and Devonian rocks of the basement of East and South Australia. The sampling workshop brought together the Geological Survey South Australia, Geoscience Australia, other government departments and MinEx CRC researchers to add value to the data collected during the sampling program and provide insights to the drilling samples.
The two-day sampling workshop focused on summarising our knowledge from different aspects of our work, from sampling strategy techniques to geochemical and geochronological data, high-logger data, and an overview of the core and chips. The workshop included contextual geology talks, viewing of the core samples and chips, the work the Geological Survey has done up to date, planned research activities, and research opportunities for MinEx CRC participants. Research opportunities include potassium-argon geochronology to date timing of alteration, as well as low-temperature thermogeochronology, such as argon-argon to date timing of alteration, exhumation and uplift. Rubidium-strontium geochronology to date fine-grained rocks, determine the age of post-Delamerian sedimentary basins, heat flow and petrophysical properties to characterise rock physical characteristics and help refine geophysical models, chemistry of pyrite and zircon to characterise fluids, the chemistry of seawater and its impact on elevated base metals in the transition from the Murray group to the Renmark group, and tracing sulphides in the back arc Delamerian rocks through to the porphyry-style Adelaide Rift Complex rocks. The Delamerian NDI sampling workshop enabled the Geological Survey of South Australia to connect with MinEx CRC research participant organisations in order to further expand our knowledge on the formation of Delamerian rocks undercover. This information will help discover potential economic mineralisation beneath deep sedimentary basins through innovative drilling technology and the successful development of sampling using the CT rig.
Today, we would like to introduce Woody Woodpecker. That is our discrete impact drilling equipment, designed to gain better understanding of the processes that control performance in percussive drilling. Efficient adaptive control requires an efficient model of the system, meaning an understanding of how control parameters affect the drilling response and how change in rock properties or bit wear affect the response.
In percussion drilling, there is both laboratory and field evidence of the existence of a sweet spot, or in other words, an optimal thrust or weight on bit applied on the drill bit or drill head that yields a maximum rate of penetration, and beyond which the performance or the rate of penetration start to drop. In fact, during the first field trial of DTROL, our monitoring equipment in Pilbara, we did confirm the existence of a sweet spot in RC drilling. We actually did prove that the drillers were operating under excessive weight on bit for most of the time, with rate of penetration about a third of the optimal rate of penetration. There is, however, no consensus on the root cause or causes for this ideal drilling condition. The question really is, does the sweet spot stem from the intrinsic nature of the interaction between the drill bit and the rock formation? Or in other words, if I press the bit against the rock surface under a given static force, and I add on top of it an impact force, does the penetration exhibit a peak value for an ideal static weight on bit? Or is the sweet spot the byproduct of the overall dynamic of the system, which includes not only the bit and the rock, but also the hammer? In other words, is the sweet spot partly controlled by what is happening between impacts? And this is where Woody comes into the picture. Woody is quite a unique and novel experimental setup that is designed to drill with an actual standard drill bit by successive or discrete impacts. Woody allows us to control the static weight on bit, but also the impact velocity of the piston or the energy of impact, and to increment the angular position between the bit and the rock, and thus to be able to propagate the borehole, drill the borehole one impact at a time, and again, without the hammer dynamics. There's actually been in the literature experimental work dedicated to the study of discrete percussive impact drilling. Most of it was done in the 50s and 60s, where people were mostly concerned with stop hammer. But most of the work has been done without the ability to apply weight on bit, or the ability to impose successive impact, with very strong consequence on the robustness and the repeatability of results, as the author tended to consider just one isolated impact, and most often with the bit against a flat rock surface, a geometry which is of course quite different from the interfacial geometry between the drill bit and the rock as we drill a borehole.
Woody has a range of quite unique measurements with uncommon sensors. Bit penetration during an impact occurs over about 1 millisecond. We therefore record at very high sampling rates the bit penetration with special laser sensor. We also record the piston velocity right before impact and the rebound velocity with high-speed proximity sensors located along the hammer barrel. But we also measure the elastic wave propagating through the bit shaft at gigahertz, which allows to track the energy transferred to the rock and reflected to the bit. We have added many automation features to the equipment that allows us to perform from 4 to 5 impacts per minute. Note that in order to initiate and propagate a borehole over sufficient distance to yield a reliable and robust measure of the average penetration per impact, we need to carry out about 150 to 200 impacts.
We have already carried out 3,000 impacts with remarkable results with no equivalence to our knowledge in the literature. With these experiments, not only we aim at unlocking one of the mysteries of percussive drilling, but also to outline the strategies to optimize drilling performance in percussive drilling.